Okay, sorry about the delay. Sorry about the delay. Sorry about the delay. Okay, hello, hello, hello. Good afternoon. Wow, fat. All right, good afternoon. Wait, hold on. Sorry. Good. Yes, good after. It's all about the chat. It's all about the chat. It's all about the base. Good afternoon, Gabriella. Good afternoon, Brian. Good afternoon, Yanelli. Good afternoon, direct chat person. Good afternoon, Natalie. Good afternoon, Kaya. Oh, there's Kaya. All right, now we're happening. I mean, without a Kaya animation, what? Hi, Annie. Excuse me. That is not about it. Good afternoon, Genesis. Good afternoon, Ariana. Good afternoon, Chastity. Good afternoon, Brandon. Okay, why? Okay, okay. And good afternoon, Kaya. And good afternoon, Chastity. And good afternoon, Brandon. And good afternoon, Yanelli. And good afternoon, Skylar. To the Wait, what happened to Gabrielle? Oh, okay, okay, yes, okay, okay. So we want to get back to this midterm. Again, quick overview. Where were we yesterday? We were Yes. So wait, and you guys remind me again, please. You have lab Friday, I believe. Remind me. I think you have lab with Mercedes with Tally on Friday. Is that correct? Yes. Okay, great. Thank you. Yes. So just to remind you again, like I don't it's not that I mean Professor Tally is like not going to get up at the board and like walk through anything. Like mostly it's going to be time. This is my understanding. It's whatever she says goes, but my understanding is that probably mostly you're going to have time to work on this practice exam as individuals and then time to work together as groups to help each other on the practice exam. And mostly that's what's going to happen in the lab. So it's not that you're going there to get answers as such. Although, again, I mean, you could ask her any question and she's allowed to answer any question. I mean, I think, but that's up to her. But you're not going to like get new information. You're going there to have a ton of time to work on this and to benefit from being with one another to work on this. And I just want to, and I think that, and I want you to know that going in, like to manage your expectations, like what it is time to work on this, to work on the practice exam. But then please do know, I firmly believe that with the actual exam, when it's posted, it's really in your interest to have done a rough draft and then a final copy type of thing. Like it's that type of exam where it's more like a presentation, right? I know I've said this, but presentation matters. Like you want to make it a very readable, clear, comprehensive document. And in the past, it's been very clear who sort of has done a draft and then who finalized it nicely. Um, and so the exam when it's posted will be similar enough to the practice that you should consider any time you're taking during lab on Friday, writing stuff like consider that you're doing your rough draft of the actual thing. Of course, you'll make adjustments, because and you'll read the new questions carefully when I post them Friday. But if you've really already done a full draft of the practice exam and your friends helped you and stuff like that, and you helped your friends and stuff like that, that is like a rough draft that you will then tweak and adjust, and finalize as your final copy for me due next Wednesday. Okay, so what I'm trying to make clear is that's how your mindset going into Friday should be like, I am now doing a rough draft of my actual exam. Like that's how you should think of it. And okay, that's my advice. Um, okay, that said, I'm going to continue trying to address. Yes. Okay. I'm going to continue trying to give you whatever guidance or hints or guidance and hints I can in this last period about the practice exam. Um, what I have some things in mind that I still want to tell you about it, but basically my strongest suggestion in a minute, I'm going to say my strongest suggestion is that you ask me questions this period. The more specific, like this more specific and focused and concrete you can make your questions, like in part three of problem four, like what do you mean by velocity or whatever. The more specific you can make your questions, the more of them I could answer this period, and I will. I the broader they are, the fewer I can answer. Um, so I suggest you ask me questions this period and I answer them. Of course, if you run out of questions, I know what I'll talk about. But let me also say, I I'm going to very try my hardest to focus on answering questions and saying things to you that I did not say in the last period, the other section of this class. So I think I already posted the video of that class to your Google Classroom. And then of course I'll post yours as well. I'm telling you that I'm deliberately trying to say different things to both classes so that I can cover as much ground as possible. So when you're studying or when you're preparing, like I highly suggest that you watch both of these videos. Is okay, and that's also a polite way of saying like I'm going to assume that I gave you this material, even if I gave it in the other video. So you get what I'm saying. Okay, so I mean, so for example, I'll be blunt, like the pendulum problem, TikTok problem three. I talked about extensively this morning in the other section. You should watch that video. I mean, I give a lot of hints and everything. And in fact, I give like a full solution for like most of the problem. So you should watch that video. I will upload that PDF to you as well. It's all going to be part of one big PDF. So I'll give you the notes, okay? But then I'm going to try today not to talk too much about the pendulum because you've got access to that. Okay. So let me pause and say, uh, please ask questions in the chat, privately or publicly. Please put questions in the chat. And again, if I can't, I mean, it's good for me to see all your questions, even if I can't get to all of them, or even if I say that's too big of a question for me to answer right now. I mean, it's helpful for you to know that I know what you're concerned about before I post this thing. So I'm going to pause literally. Um, and I want you to like leaf through the practice document, which really is practically the document. Um, and see where you have, and I'm not going to answer questions until I see like about three of them or at least in the chat. So, so please have at it. Oh, okay. I see. There's one question in the chat. Great. Very legitimate question. Very legitimate question. Um, I'll read it out loud in a second, but I don't want to influence other people yet, but yes, there's only one question to chat. So if you wrote a question to chat, you know who you are. And that's a very fair, and yes, the answer is yes, I will. But I want to see how much time I budget for that, like based on the other questions. But yes, person, yes. I mean, good. That would have been, honestly, that would have been my agenda item. That is my agenda item. Um, okay, but I'm still gonna wait. I want to give you a little time to, one person has asked a question. Oh, two. Okay, well, that's honest. Well, someone wrote, I don't have a question at the moment. Well, thank you for at least, all right, fair enough. I'm gonna wait like a minute more. All right. Well, okay. I, I'm a little, I feel like I've gotten like one question in the chat and one honest. I mean, look, I mean, obviously if you're good, you're good, but, uh, oh, all right, let me see, because I don't want to, okay. Okay. There's no, you could keep the questions coming. Like this isn't the cutoff. I'm slightly nervous that there aren't more questions. I don't know what that means. I mean, I'm slightly nervous that there aren't more questions, but okay, I don't want to, force anything. Um, you could still keep them coming. But the one question that's in the chat right now, um, is could I talk about question four, pulse? So that is a very fair question. Like that is definitively the one thing I've not spoken about. I mean, this week, and I didn't speak about in the other class. So for sure, that would be my agenda item. I will. To be really honest, the reason I'm stalling slightly or the reason I'm waiting till there's other questions is because that's a big enough thing that like once I go into that, it is possible, that I'll spend a lot of time on that, and that's good, but that won't do anything else. So I mean, I'm happy. So it's kind of a warning. Like the plate is going to get kind of full if I start going down the road of question four. But yes, okay. So I'm talking about question four. Um, I think also what I'm going to do. Again, please though, watch the other video to hear more about the pendulum, where in fact on the pendulum, I learned in the other class that if you went to the MSRC review, there was something they did in the MSRC review about the pendulum that I would do differently. So if you went to that, like, and there's something that I kind of straightened out in the other video, you may want to check that out. But the other thing is, in the other video, I at the end give more hints and insight about the Doppler effect business. So you should check that out. But so now, I mean, if all that is there, I'm going to go to question four now. I'm going to switch the screen share. I'm going to switch the screen share. Wait, am I? Where is the? Yeah, I'm switching the screen share. Okay. Okay. This is question four. This is a big question. This is a very open, I mean, the reason that the sort of grading rubric is so specific here is because, yes, this is more, I mean, this is a very open-ended question. It's telling you things that your answer has to have in it to be a full answer. But yeah, you're going to, like, it's like an essay, you're going to walk me through, kind of a big explanation. Um, Um, so yes, you want to make sure that your explanation it contains all of these elements that it's asking for. And again, before I get rolling on it, I'm gonna try to like do a little walkthrough here, and then I'll go to the, writing down on the board. But again, let me say this one, I promise you there are full extensive videos where I literally walk through it or what I'm looking for from top to bottom. And for past semesters there are, and often they're literally called problem four or like pre-midterm or something problem four. Like this is always problem four. I don't know why. So like you really can find an extensive walkthrough of this. And I suggest that you do. Also, I want to remind you that it's not meant to be out of nowhere, but furthermore, it is. I think I mentioned this yesterday. Sorry. This is asking you to show that you understand a thing that I did explain extensively to your class this semester, and the video from this semester is called Staggered. No, it's called Staggering. It's like a pun, but whatever. It's called Staggering. So like that, if you play that video, like that's what I'm looking for. This is not supposed to be a trick or a surprise. It is supposed to be, but it is like it's like a hard concept that I explained to you. Now I want to see you explain it back to me. Okay, it's not a trick. It's you got so play that video for sure. Now I'm still going to do it right now, but and I'm not trying to say don't you already know this. I'm not saying that, but I am saying don't overthink, don't overread into this. Don't think it's like a new application of something. It's not. It's just makes it would be like if you were in an AP bio AP. Did I just say AP? It'd be like if you had a bio exam and they were like explain the Krebs cycle. You know what I mean? Whatever. You get my point. Which I couldn't do to save my life. But okay. So it says show how the propagation of waves can be understood as a properly arranged collection of properly properly arranged. Okay, of properly phased staggered harmonic oscillators. And then, first of all, it's looking for clear, detailed, and fully labeled diagrams. Okay, the first diagram it's looking for, I mean, again, I might switch screens in a second and draw, but the diagram that you want to start with for this question is not a graph. Don't start with a graph. Like definitively do not start with a graph. You want to start here with that picture that I once gave you of like a spring hanging down with a block on it, and then next to it another spring hanging down like low with a block on it lower, and another spring hanging lower than that with a block on it like that. And they could be hanging or they could be whatever. They could be sitting on a table, but the picture where you have a whole horizontal arrangement of vertical springs, that's the picture that we're talking about here. And all the masses are like at different points that are going like that. Like that's what I'm talking about. Again, I'm not asking you to be creative and come up with something new as such, but I am asking for you to understand that picture and give me your version of it. And yeah, you're going to fully label it. What do you, and again, stop me if it's too abstract and I'm saying this in space without drawing it, like let me know. But I just feel like I can cover more. You, believe me, you have that picture in your PDFs and stuff like that. And what are you going to do in the label of that picture? Really, the labels. First of all, every single mass you want to label with like a little M, and every single spring you want to label with like a little K. And part of what you're doing when you label every spring with a K and every mass with an M is you're getting across that these are identical oscillators, like they have the same parameters, and therefore we will have reason to believe that they will all oscillate with the same omega, right? So you have a bunch of masses like lined up, lined up like that. Each one has an M and a K, same M, same K. And then for more than that, you're gonna superimpose or put in the background like an X-axis and a Y-axis. Okay, like different color, dotted lines, something. In the background, there's an X-axis and a Y-axis. And first of all, the very first spring you draw really should be right on the y-axis. I mean, that's my advice. And then right, and then each spring from there will like be arranged to the right of the y-axis, and they should be at equally spaced intervals, right? So you're going to label an axis x and label an axis y, and these axes are like measured in meters. I mean, this is like literally spatial axes. So x in meters, y meters, whatever. Um, and along the x-axis, put little markings like 1, 2, 3, 4, or as in 1 meter or 0.01 meter or whatever, and 0.02 meter, whatever, and sort of have it be clear that each one of your springs is at the next centimeter or the next meter or whatever. Okay. And furthermore, again, furthermore, you could put little labels then, or somehow indicate like that, therefore this spring that's at the 0th mark, that's on the y-axis, that's therefore our 0th spring. And the one that's 1 meter away is like our first spring, and then our second, and then our second oscillator, and our third oscillator, etc. So you're labeling each oscillator, you're making it clear that they are oscillating along a y-axis, but distributed along an x-axis, and they're distributed evenly along that x-axis. Like, these are all sort of requirements of the situation. And furthermore, if you sort of do this, I think, again, there's room to sort of handle this drawing different ways, but there are some basic requirements. And another one would be that I think if you're trying to do things in the most sensible, clear way, some of these masses would be above the x-axis and some would be below the x-axis. Like, if the masses are at that moment in that snapshot arranged in a curve like this, that curve would fluctuate, would oscillate up and down evenly around the x-axis, and the x-axis would be where one or two of them are. Stop me if I'm not making sense, but right, like, don't. Okay, so some of the masses are hanging down below, some are hanging above, and if you're careful and wise and neat about it, they're not only at sort of even intervals horizontally, but where the masses are in the cycle sort of is in a pattern based on where they are in the x-axis, right? In other words, that's what this thing means when it's okay. So the ultimate point is when it says properly phase staggered harmonic oscillators, what we really mean by that is that they're staggered in phase by a constant amount while they are distributed along the x-axis by a constant amount. That's what we're really saying, right? And by the way, everything I just say vocally right now is hints and suggestions of things that, if you get what I'm saying, these are things that you would write down or make clear to me that you get. Please always remember, the minute you get something, it's very tempting and easy to think, oh, that's obvious because I get it. And therefore, that's not what he's looking to hear. The reverse. Anything you get, especially if you think it's obvious, I promise you, other people don't think it's obvious, and you might not have thought it was obvious 2 days ago. So anything you get that I'm saying is things that you would try to make clear to me in your presentation of this. So the thing I'm saying right now is that the oscillators are distributed uniformly along the x-axis, but their phase constants are distributed uniformly also. Therefore, their phase constants are distributed uniformly with respect to the x-axis. Meaning, and if you look back at the drawings I made, that most of you are better at drawing than I am, or at least you're going to be more careful because it's your final copy. If you look back at the drawings that I have in the PDF or whatever, that's what I was trying to do, right? Like, my very first oscillator maybe was at amplitude position, like all the way up, as high as possible on the y-axis. Then the next oscillator maybe was at equilibrium. Then the next one was at negative amplitude position. Then the next one was back at equilibrium. And then the next one was at amplitude. Like, you want to do something like that. If you really, I tell you, it would be really ideal if you went twice as many as that. Like, if you, right, if you, anyway, but you understand what I'm saying, I think. So you draw, that's the drawing. That's the first drawing that I'm looking for. I'm just pausing for a second. I'm just okay. Clearly detailed. Now there's more diagrams to come. There's eventually going to be graphs and stuff, but that's what you start with. Um, and the pre and the whole idea behind this whole thing, I'll say this more as we go down. The whole idea is you're trying to show, I mean, it says it, but you're trying to show how we build, how we, either Mother Nature or we in the lab, build wave pulses from collections of oscillators. Like the principle here is that you put oscillators together in a certain way and you get a wave pulse. That's what you're trying to show us physically and mathematically. Um, so that's why your first diagram here is your first thing is a bunch of oscillators. Like, but when you present that diagram, it's just like when I presented it in class to you. Like, we don't yet know anything about waves. We don't have waves. We just have oscillators arranged in a certain way. The certain way being phases staggered by an amount that is constant relative to the x-axis. But okay, so that's the diagrams. That's part A. Now, B, clear, correct. So that's the first diagram. Um, B, clear, correct, and persuasively presented mathematical equations. So, yeah, and then specifically like original position function for each individual oscillator. Like, what is that? Okay, again, if you look back at our stuff, this is that like for the zeroth oscillator, you could write down why. So I'm wondering if I should switch to the. Hold on, let me just. Sorry, I'm looking at the time. I'm just trying to make a decision whether this is better if I write it down or keep talking like this. Very quickly, if anybody's still listening to me in the private chat, anybody who's hearing me right now, could you just put down, like, honestly, would you prefer for me to keep talking or for me to draw while I'm talking? I mean, but to keep talking while you can see the thing I'm talking about or to draw while I'm talking, just put in the private chat if you have a preference. Okay. Well, that was pretty direct. Wow. Okay. Well, that answers that. Okay. I'm glad I asked. Okay. All right. I'll do it right now. Good for you for saying, yeah, yeah, okay, everybody, and thank you for being private about it, because, but every single one of you just said the same thing. So, wait, oh, oh, you can have the midterm on a separate tab while good point. All right, fine, great point. All right, so I'm switching. Bear with me for a second. Thank you for being honest and fast about that. Just give me a second. Yeah, you're right. You can have it on a separate tab. I never think of that. I'm so self-centered. Oh yeah, okay, okay. So I'm going to draw. Notice all these notes, and this is all the PDF from the other class. I'm just going to pick up. I'm just going to so you'll get this whole PDF, okay? And they will too, obviously. So this is what I'm talking about. Okay, this is what I was just trying to say. So yeah, you're right. This is much better. So I'm just being okay. So this is what I this is a diagram to start with. Like this is it. Okay. Pro tip. I mean, if you really want to blow me away or really want to make this like I would do twice as many. Like in other words, have a mass in between the equilibrium and the top, and a mass in between the equilibrium and the bottom. Like if you really want to, but this is the idea. Um, and I'm going to say this when I get, but notice if you know what's going on, one way you can know that you know what's going on is in this case, the, I mean, I'm sort of jumping the gun here, but the step, the phase step in the way that I just drew that, like you can physically see by looking at this picture that the phase step is pi over 2 radians per meter. I will say that more specifically like later on today, but as a little test to your, as a checkpoint to yourself of like whether you know what's going on, like even though I didn't put any numbers in this, you literally can see, from the picture that the phase step, the K, the angular wave number is pi over 2 radians per second. I'm saying that because each one of these things is separated by a quarter of a cycle from the next door neighbor, right? And I say quarter of a cycle because a full cycle is all the way from amplitude to negative amplitude and back. So a half cycle, that's 2 pi radians. So a half cycle is from amplitude to negative amplitude, but like not back. So that would be pi radians. So from amplitude to equilibrium, or the equivalent, that's pi over 2 radians, right? So each one of these is separated by pi over 2 radians. I'm just saying, if like you're understanding what, and I'm recommending to you, if you get it and you're looking for how can I, knock Yavarom's socks off and like get an A plus 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 plus, whatever, you might want to make a picture where the angular wave number was like pi over 8, whatever. But okay, so this is a picture. This is a picture I'm talking about, something like this. Then it says provide provide a separate equation for each of the things. A single, an original position function for each individual oscillator. So what's that talking about? What it's talking about is this. All right, so this is 1. 2 is something like this. Right? I mean, and in my case, right? Like, stop me if I, and so on. Now, again, I'm giving you the information here. I'm just trying to remind you of the physics. But like you're going to talk about, like you're going to explain it while you go. You're going to add English and all of that, or different colors, etc. But this is the basic thing that I'm talking about. And really, this is like an essay. You're going to walk me through. But here's what I'm talking about: the elements that it's asking for. These are the position functions that I mean. And again, like you will know that you really understand this if you could see why specifically that I put pi over 2's in each one of these parentheses, right? And if you made a different diagram, like you would have a different constant in there. And the more original your constant was, the more you'd be showing me that you really get what's going on and you haven't just memorized this, or not even, and you're not just copying this. You know what I'm saying? So like the first oscillator obeys that equate, the zeroth oscillator obeys that simple harmonic oscillation solution. The first one is a cosine omega t plus 1 over pi over 2. And then the next one is a cosine omega t plus 2 over pi over 2, because they're all being measured relative to the 0th one, if that makes sense, right? Um, so you'd write something like that. Um, Numerical example. Then chew. Wait, sorry. Oh, no, that was B. I'm sorry. I'm sorry. Hold on. That's B1. And so this whole picture is A. Okay, and I know I'm wrapped. Can I just say again, this, the problem itself is like a grading rubric. It's telling you the elements that you have to have in order to get all the points that you want to get. But it's and yes, it's probably a pretty helpful guide to like the order in which you should think about things. But please understand again, you're not just bullet pointing these results. You're trying to make a coherent presentation out of this. I keep saying that because I'm like worried. This is the problem of why I don't want to like literally give you an answer key to the whole midterm, because then it almost deceives you into thinking that if you just copy it and give it to me, that that's what I want. That's not what I want. I want you to turn this into like an essay. Or, essay is a bad word, but like a lab report. Oh my, what a report. You know what I'm saying. Just please bear that in mind. That if you just literally copied this PDF, that would not be sufficient. But okay, so those are the equations B1, B2. Um, Numerical examples provided for the equations in action. Um, um, that means something like it, like that. In fact, hold on, let me back up. I'll explain that. But that just reminded me in this original picture where our labeling everything, you know how I always say in physics, well, there's one thing that you could be labeled here, like I could have or should have put a little label right here, this y-intercept, this place in the axis. That's what we mean by the value A, right? The amplitude, like the highest any mass ever gets on the y-axis is what we mean by A, just to be clear. So, like, what these equations mean is that, for example, sorry, for example, the zeroth oscillator at the when time equals zero, because the phase constant for the zeroth oscillator is zero, then at time equals zero, the zeroth oscillator is at A, whereas the first oscillator is at A cosine 0 plus pi over 2. So the first oscillator is at A cosine of pi over 2, and the cosine of pi over 2 is 0. You see, so it's like another checkpoint. It's like you're showing how your equations actually are consistent with your diagram, because each one of the oscillators is like where we think it is based on those equations. That's what I mean by numerical, something like that. Again, the more different your example would be from exactly what I just did, the more you would show that you actually know what you're doing. But that's the kind of thing I'm saying there. Then three, a single position function to capture the entire collection of oscillators. Well, something like this. Oh, well, sorry. In this case, and this is again, if you look back at this is exactly how I did it in the, I mean, not exactly, but something like that. Hold on, I'm going back to the chat in a second. So I'm in three screens at once right now. So forgive me if there's something in the chat. I'll see it in a second. Um, okay. Well, I'm looking at the chat. Okay, there's nothing in the chat. Okay, so this is now where it starts getting sort of important. I mean, three, like the equation I just wrote captures this situation. I hope you see that, and if you don't, please ask. But I'm saying like if you wanted to know how, if you want to do this plug and chug thing that we just did in B2, if you wanted to see based on this diagram how high any given mass was at any given time, like if you wrote down y equals a cosine omega t plus pi over 2x, like that means as long as you pick a certain time and you pick a certain os, if you plug in a certain time for t and you plug in the location of a certain oscillator for X, like the seventh oscillator is at the seventh meter position. So you'd plug in 7 for X, for example, right? If you plug those two things in, then this will spit out exactly how high that oscillator is, because the whole idea is that for every next oscillator that you move over, you've increased the phase constant by that many pi over 2 radians, right? I mean, so this is like the general expression for the pattern of the equations that you just established when you wrote one at a time. But so the point is that this would be true for this case where your oscillators are staggered by pi over 2, right? But what you then want to show me is that you understand that's just a particular example. And again, I cannot emphasize enough that if you're really following me and you really want to show me that you really understand, I highly encourage you to pick a different example, make a drawing that is a different example other than pi over 2. Now, the reason I keep doing pi over 2, to be honest, is it's the easiest, it's probably the smallest number I can do that still makes the point clear. Like anything smaller wouldn't be clear. And anything bigger, like, takes a lot of time to draw. But it's your exam. So I would recommend doing something like pi over 8 or something, so you can really show me that you get what's going, you get, okay, but whatever. I'm doing pi over, what did I just say? Pi over, oh, or even do pi over 4. I mean, I'm sorry. If you even do pi over 4, you're really showing me something. But I'm doing pi over 2, a quarter of a cycle, right? So what it's getting at in part 4 of problem 4, what it's getting at is, well, it asks, what's an explicit explanation of how or where angular wave number arises and what it means? Well, so this is where you say something like, okay, now again, these are my words. You want to use your own words. You need to use your own words. But what I'm saying here is like, okay, now we pause and we say, look, the pi over 2 thing, that's like an example of how to stagger. Well, what I wrote is, but pi over 2 was the phase step only in this particular example. In general, the oscillators could be staggered in phase by any constant amount of radians per meter, right? Like, that's the key point, is that what we do need to do is to follow the instructions of this setup. What we do need to do is stagger the oscillators in phase by a constant amount, and a constant amount that is like keyed to their horizontal arrangement. That's what we need to do. But there's no rule that that constant amount has to be pi over 2. Pi over 2 is just an easy example to draw. So it could be anything. That could be anything is the phase step, the amount by which we increase the phase, the amount of radians by which we increase the phase every meter that we walk along this arrangement, right? So the phase step could be any constant amount of radians per meter. Sidebar, any amount literally means any amount. I mean, the phase step could be 2 radians per meter. It could be half a radian per meter. Like, there's no law that says it has to have a pi in it. It's just that if it has a pi in it, it's like easiest for us to picture because there's 2 pi radians per every full cycle. But I mean, it could be any number of radians per meter, right? So we're now going to say, fine, if we're going to generalize, thus, in general, I just switched wrong color? Well, thus in general, let K be that amount of radians per meter, right? Let K be that constant amount of radians per meter, the amount by which you stagger the phases, right? And we'll call it from now on the angular wave number, such that now in general we can say y equals a cosine omega t. And every time I was saying plus, it could have been plus or minus. Well, it was plus. Well, sorry, it was plus in this case, but it could be plus or minus. Like, so now I'm swapping out the specific pi over 4 and putting in the general term K. And it's K with serifs on it. Like, again, do whatever you want, but it's not the same K. It's not these Ks. That's a different, okay? It's a different K. So now I could write that. And here, okay, what I'm, again, pro tip or whatever, I'm now saying at this point in my explanation, now that I've gone from the specific setup with the pi over 2 or whatever, and then like talk about how pi over 2 could have been anything. So I gave it a name and I called it K. Now, two things are happening. Now, first of all, now I'm saying the reason K is called wave number is because now, once there is a K involved, once there is this constant phase staggering, now we have a wave pulse. Like what do I mean by now? I mean it wasn't a wave when it was a cosine omega t plus some constant. Any one of those individual equations was not a wave. Any oscillator by itself is not a wave. But when you put together a whole bunch of oscillators, and each one of the oscillators is a cosine in time, but you arrange them all so that they make a cosine in space, the way to capture that idea is in this one big equation that doesn't just say a cosine omega t plus some number. It says a cosine omega t plus some number times x, right? And that some number we call k, right? Once you have a function that is dependent on time, once you have a cosine expression that's dependent on time and space in this way, once it has omega and k in it, now it's a wave. That's why K is called the angular wave number, but that omega was not called angular wave frequency or something. Like it was just angular frequency. It wasn't a wave then. Now it's a wave because it's cosines in time and in space. So I'm yelling two things. One, this is where you expand. Like I'm not doing it for you here. I mean I am vocally, but I'm not on the page. Like this is a point. Whenever you introduce K, when you introduce K or show like where K came from in our lives, where the angular wave number, that's when you stop and in your way and go as crazy as you can. I don't mean crazy, you know what I mean? Go as expansive as you can. Explain how this is now a wave pulse. Like, honestly, I would encourage you, again, not only to like watch the videos and blah, 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 but like take a little side path and remind me, like I did with you in class that day, Like, remind me what you mean by wave in the first place. Like, what is a wave? A wave is, oh, like wave motion from place A to place B means motion that occurs from A to B, but for which no individual no individual particle makes the journey from A to B, right? Like, you might take a little side path and like remind me what is ever meant by waves in the general context, like water waves or something. And now, or like on the string in lab 3 or something. But and then now you say, but see here, if you stand back and you look at these things that each one of them is going up and down, up and down, up and down. So now we have a pulse traveling. Like, now that, in other words, that picture, this picture is just a picture. This is like your y equals x graph from lab 3. This itself is not a wave. It's a cosine in space. And one of these oscillators going back and forth is not a wave. That's a cosine in time. But if this whole thing is in motion, if this is a frame of a larger movie, where each one of these, where this cosine thing is wiggling up and down in time, so that we can, then it's a wave, right? And we literally know it's a wave, or we can see this wave because the trough that's here at point 2, right? In my picture, the trough, like if you were watching this in the lab as it was happening, that trough would be moving along horizontally. It wouldn't be staying at location 2, right? And you want to explain that in your words now that we have multiple oscillators staggered in phase by a constant amount. Now we don't just have oscillators, we have a wave pulse. We have something that's we have a recognizable shape that is moving along the x-axis, whatever the shape, like a crest or trough. We have a recognizable distortion or disturbance from an equilibrium, right? Like equilibrium would be like just a bunch of horizontal mass. I mean, a horizontal bunch of masses just sitting there. But we don't have that anymore. We have crests and troughs. And more to the point, the recognizable crests and troughs are now flowing from left to right. And tell me that. Yet, no mass is flowing from left to right, right? That's what makes this a wave. And mathematically, what the key to it is that now we have an angular wave number called K. Okay, so number one, I'm looking at the time. I'm saying this would, at that moment when K somehow gets introduced, and again, you might do this in a slightly different order, although I don't really know that you could do it in a very different order, but you do your language, your pictures, your handwriting. But by the time you get to this stage in the discussion, when you introduce K, that is your opportunity to really explain to me how this thing is now a wave, which is the point. That's number one. And number two, I don't know if this is a pro tip or the reverse of a pro tip, but I can tell you from experience, from grading experience, that on this question, what separates the correct good ones from the ones that don't do well is like anybody who's using K earlier in the problem before this point is misunderstanding the situation and getting it wrong. Like, on one hand, I'm saying once you introduce K sort of in the middle of the problem like this, that's when you want to make a big deal and like have trumpets and fanfare, that's when you want to make a big deal and say, now we're talking about a wave here, folks. But the converse is also true. This is why I say don't start with a graph and don't start with any equation that has a K in it. People do it all the time. So, I mean, it is a pro tip it's a reward for paying attention right now. If the beginning of your problem, if you treat as a given some equation like y equals a cosine omega t, this equation that I just wrote, hold on, sorry. Yeah, the equation that's at the bottom here, it's very on purpose in my mind that I didn't get to this until like 3 pages into this discussion. If you start with that, you're misunderstanding you're misunderstanding the whole thing. Similarly, if you start with a graph or two graphs or like wave graphs or something, you're misunderstanding. We're trying to derive or build a wave from oscillators. So you start with knowledge of and pictures of and equations of oscillators, and you get to K. So you'll know. So, okay, I'm going to move on, But literally, if we were just doing an overview and I wasn't drawing this out, or like in another class, I said the key to this whole thing, you know that you're on track and you're kind of doing what we're looking for here, is if you view this as sort of like, can I walk a reader through no knowledge of K into knowledge, into clear knowledge of K? It's really about bringing K out of the hat. Like that, that's what this is about. Okay. And that's like how when I'm grading, if especially if I'm grading fast, I literally am looking for like how early is K in their discussion. Okay. Um, so that's that. Then I mean that as advice. I don't mean that to scare anybody, but um, okay, but that's that. Okay, so that's part four. Okay. Oh, and that's C. C, I just like C says clear, detailed, and thoughtfully crafted verbal explanations, transitions. That's what I'm talking about. Everything I just said. Okay. Then, okay, final position function. How much more do we looking at? Oh, okay, okay. Excuse me. Okay. Okay. Um, right. So C is like where you talk about waves in general. Okay, then D is back to math. Um, Final position function differentiated four times. Um, I'm also going to say, so I'll show you that. Okay, we're going to finish this in time. He says to himself, uh, I'm going to show you that differentiate, or at least show you the roadmap of that. But I also want to say, like, actually, before I even do that, remember at the top it said diagrams. It didn't just say diagram. Under this whole discussion, like somewhere in here is where you also it might occur to you to think about lab three. Like by the time we did lab three, right? I just want to remind you again, I don't remember if you're up to, this is really kind of secretly lab four, this whole question and it's problem four for whatever. And and you know what's going on if you understand that this is the reverse of lab three. Lab three, you took a movie of a wave and you decomposed it into its time and its space oscillations or cosines. And here we're saying the reverse. We're saying if you put together cosines in time and space, what you get is a wave. I mean, it's the same, right? I mean, that's what we're trying to say. So ultimately, you have two more. Now you could put in graphs, is what I'm saying. Now you could put in graphs, and if you want, because now we understand that like this is true while this is true. Like they're both happening at the same time. And if you put them together, what we get, if you put them together, we get one big cosine. Let's call this is 1A, this is, they're not, well, no, they are the same A's. Sorry. You get one big cosine, right? Like that's what we're trying, sorry. That's what we're trying to say. So, so now you can think about graphs, but we didn't know that before. Now we have this one big function, a cosine omega t plus kx. So now, and that's what I mean by the final position function. So then in D, we're going to take that and differentiate it 4 times. Let me see if I can do that quickly. Well, I'm going to just do it quickly now so you can see what I'm talking. I mean, again, you want to walk me through, if you use chain rule, either explain it or say chain rule C above, whatever. But first, I'm going to differentiate with respect to time. So I'm going to do it with respect to time, and I'm watching the time. We have 12 minutes. I'm going to differentiate with respect to time, which means holding everything else besides time as a constant, right? So I get like, and then I do it again, right? So that's the partial derivative of the function with respect to time. That's two derivatives. Then I do the same thing, but for space, for x, right? So, and again, all this, we've done this and you did it in lab, but so I do now I treat x as the variable and I hold t and everything else constant. So I get, well, okay, whatever. I could cut to the chase. I should cut to the chase, but right. And what's the point of all this? Then uh, I'm just looking at the time. Well, yeah, no, all right, we're okay. Yeah, we're well. Let me look at this. If there's any, we're fine. If you really don't have any other questions, I'm going to finish this. I mean, we will finish this in time, and I mean, I won't do anything else. But if you really don't have any questions, I'm happy to now. I'm happy to finish it. Okay, I guess I am. I mean, this is sort of last. I don't mean. I mean, if there's any other questions, you might want to sort of put them in the chat now. But other than that, what do I do now? Well, same thing I did in class. Like I rewrite. I'm trying to get the one derivative related to the other. So I rewrite one second derivative related to the other. So I rewrite each one. I realize that that parenthesis is the same parenthesis running through everything. All right, so like I have for time, I have this, right? I'm just recopying it. So I recopied it. So I'm going to divide both sides by everything but the parentheses thing. So I'm saying, and I can do the same thing to the other function, to the space. I'm just going to skip a step and do it. So the space also equals that cosine thing. So equals, I mean, so both of them equal the cosine thing. So both of them equal each other. So therefore, if you want me to go back, I will in a second, but therefore I'm saying this. Right? So the negatives cancel out, the A's cancel out, and I have at the end of the day, right? It's 412. And that's bit. That is the second order partial differential equation that describes all one-dimensional wave pulses, like all. And by one-dimensional, I mean wave pulses that are propagating along a one-dimensional medium. Lab three, like crests and troughs that are flowing back and forth along one long line, like one long medium that would just be like a line, but for the pulses. So that's the one-dimensional wave equation. And that got derived. What we're trying to show in all of this is that these waves that are described by that partial differential equation got derived by putting together a bunch of oscillators, a bunch of other differential equations, to a bunch of time oscillators together in space in a certain way. You get that, right? And you're going to put that in your words. We're almost done. But that's the wave equation. Yeah, so that's part D. Um, part E, okay. Part E says compare, contrast that to simple harmonic oscillation, right? And this is what was on the board. This is like the grand finale conclusion of like our whole life to this point in the course. And this was what was on the board. If you look back at the PDFs, what was at the front of the board yesterday was this equation underneath the very similar one for harmonic oscillation, another which I'll go right again right now. Like this was on the board yesterday. This versus this. Sorry, I do this every time. I mean, that's correct, but it looks better. Okay. Um, right? Like the top equation is the differential equation, the second order, ordinary differential equation for simple harmonic oscillation. And then the equation under it is the second order partial differential equation for wave propagation, for 1D wave propagation. If you what it's asking you to do in part E is like compare and contrast. Like, and I'll just say this verbally. And again, I've said this, like, like, like they're so similar and yet different. The left side is identical. Like, why did the symbols change? Because remember, remember, simple harmonic oscillation is a function of one variable, but wave propagation is a function of two variables. That's why the derivatives became partial derivatives. But if you look at the left side, it's the same thing. In either case, and the top equation is like assuming like a vertical spring, right? I'm just trying to be balanced in my comparison. The top one is saying, so I'm going to say this. You want to say this in your words. The top one, well, the top one is saying the rate at which a oscillator accelerates back to equilibrium is directly proportional to how far it is from equilibrium, right? That's Hooke's law. That's restoring force. That's the whole point of elasticity, right? The top equation says what it means to be an oscillator is the rate at which you accelerate along the axis back toward equilibrium is directly proportional to how far away you are from equilibrium. Like, right? That's what the top equation is saying. Well, the wave equation is saying something very similar, yet higher dimensional. It's saying if you pick any point in the medium for a wave, any point at all, the rate at which that particle, that piece, the rate or any mass on any of these springs that we've like spread out like this, the rate at which a piece of your metal slinky will accelerate back to the equilibrium line, the equilibrium orientation, the rate at which it will accelerate back to horizontality is directly proportional to how concave the medium is at that point, i.e., how bent, how not flat it is. You see, it's the same concept, but it's extended by one dimension or expanded by one dimension. That's what I'm asking you to explain here in E, is that for an oscillator, acceleration is directly proportional to displacement, but for a wave, acceleration is directly proportional to concavity. And if you really get how that all makes sense, like put it in your words and tell me, because that's what I want you to get. And then F, you put it all together. I mean, F, you say, therefore, I mean, for example, F might be the opportunity, these two graphs that I just sort of threw in your face, like over here. Maybe F is where you put those graphs in or something. F is where, I'm looking at the time, we've got 2 minutes. F is where you summarize like I'm trying to do right now in your words, like say, so you see, like wave propagation consists of a bunch of time oscillators spread out in space in a specific way, such that we have cosinusoidal oscillations in time and in space together in one phenomenon, like something like that, right? And literally, and you could say things like, for an oscillator, equilibrium is a position, but for a wave, equilibrium is a whole axis, is an orientation. So for an oscillator, the farther away you are from that spot, the faster you accelerate to it. But for a wave pulse, the more bent out of shape you are from flatness, the faster you accelerate back to flatness. Like literally what it means to be a wave. I'm just saying different ways of, whatever clicks for you, that's what you want to expand on. For wave, literally what this wave equation literally means is that you pick any point in space or time of that whole wiggly metal, your piece of metal in lab 3, any piece of metal at any time, it is accelerating back, if you believe it is accelerating back to flatness at a rate that's directly proportional to how unflat that piece is. That's what it means for it to be a wave. Like that's happening all over the place at all times. Everything, the more bent it is, the more it tries to unbend itself. It springs expanded into a second dimension of space. So that's the exam. Hopefully that, oh, sorry. Yeah, 5 is a concluding paragraph. You are correct. Yeah. 5 FAC. Step 5 is like a concluding paragraph. Yes. And also, you're right. Good question. I see in the chat. Yeah, and we're done. I mean, you can go. But I will say, as long as you're fully expansive and hit all the points for this problem four, right. I'm not sure that you need to literally also do a 5-step method. I mean, that's like a thing to weird thing to say right at the last minute, but if you can, great. But like the main thing, but the grading rubric is the question for problem 4. So as long as you hit all the points and fully explain it, yes. And then your step 5, your final step, is a concluding paragraph for the whole thing. Yes. But yes, you still can do the 5-step method. I shouldn't have even said what I just said. Yes, the answer is yes. Like step 5 in this case is like a culminating. Yes. Okay. So I'm done. You've been very patient. I wish you all the best and luck. And you could still text or email me with sort of concrete questions until Friday, and then not after Friday. Okay, I'm turning off the recording. Have a very nice day. Yes, have a nice day.